We already talked a little bit about the frictional force. I said that it was the parallel component of the surface force, the perpendicular component being, of course, the normal force. So that's one way that you can tell, should there be friction in this situation, whatever situation that you're looking at. You look and say, okay, are there any surfaces touching? If so, I should go track down if there's a normal force or if there's a frictional force. And you can do that by kind of looking at like, okay, how is the object moving? What is its acceleration? And what are the other forces in the situation? So the trick with friction force is look and see if there were no friction, would there be any relative motion going on or more relative motion than there is right now? So friction is the force that opposes relative motion. So if everything was made of ice in a situation and you'd have something sliding along, if that were true and it's not, that must mean, okay, if it were going to move that way relative to whatever surface it's touching, there must be a friction force pointing the other way. So that's what you should be on the lookout for, to see if there's friction anywhere in the situation you're looking at. And there are two kinds of friction. There's static, and static means still, and that means there isn't any relative motion. And in that case, the friction force is opposing the relative motion so well that it's actually stopped it. It's kept it from happening. So an example of this would be if you are pushing a piece of furniture and it's not moving. Assuming that you haven't, looked to see what was going on, you're not trying to like push it into a wall or something. In that case, it would actually be the normal force of the wall that's stopping the furniture from moving. But if you just got some furniture, out in the middle of the floor and you are trying to push it along, there we go, like that, and you're trying really hard with a force that is very big, a push force, but it's not budging, there must be another force opposing you. And so that would be the friction force between whatever this piece of furniture is and the floor. So that would be one place where static friction shows up. The furniture's not moving, so it's static. So basically what you're looking at is the bottom piece of the furniture moving relative to the surface of the floor? If not, then there we go, static friction. Another place that you could get static friction showing up where there's no relative motion would be, for example, if you had a backpack that's sitting on a car floor and the car, speeds up or slows down, forgot that word, or turns. Basically, if the car is accelerating and the backpack is still on that car floor, sitting in one place, then there must be some static friction going on. Static friction because even though both the backpack and the car are moving relative to the road, the backpack and the car floor aren't moving relative to each other. And if there were no friction in that situation, as the car speeds up or slows down or turns, well, the backpack would be sliding around the car floor back and forth. When it speeds up, the backpack would go sliding to the back of the car. When it slowed down, the backpack would go sliding to the front of the car. Or when the car turned, the backpack would go sliding to the outside of the turn. If that's not happening, that means friction is stopping it from happening. And because the car floor and the backpack aren't moving relative to each other, it's static friction. And static friction will kind of be as big as it needs to be to stop the motion from happening. But there is a maximum value. Of course, you can eventually push the furniture hard enough that it'll start moving. So normally to figure out how big friction actually is in this situation, you have to run through Newton's second law and see what all the other forces in the situation are that add up to be zero, so there's no acceleration. But if you want to know how big could static friction actually be, well, the largest it can ever be, so here we have force with the sub s because it's friction, and then a comma sub s because it's static. The biggest it can ever be is what is called this coefficient of static friction. That's a mu, the Greek letter mu, and S for static, times the normal force. So this is a maximum value. And these coefficients, you can look them up. There was a table that you no doubt saw in the textbook, table 6.1, that had a whole bunch of different values. It depends on what those two surfaces that are not moving relative to each other, what they're made of. It depends on kind of the roughness or smoothness of the surface. And it also depends on conditions. For example, the coefficient of static friction between, say, tire rubber and a road, asphalt. That's going to be very different depending on whether or not the road is dry or whether or not it's been raining and the road is wet. But this is the biggest static friction can ever be, though in general it'll be just big enough to stop that relative motion from happening. So let's go ahead and write this up here so I will have enough room to talk about the other kind of friction. The other kind of friction is, of course, kinetic, which means there is motion. Kinetic means moving, so static, there's no motion, and kinetic, there is relative motion between the two surfaces. So an example of this would be a kid sliding down a slide. And there we've got the kid and the slide are moving relative to each other. That's the whole point of the slide. But you do want a little bit of friction there. You don't want the kid just like accelerating as much as possible, as high a rate as possible. You do want a little bit of friction to slowing down. But hopefully not too much, because otherwise it becomes one of those really lame slides that you kind of have to scoot yourself down. All right, but assuming the slide actually works and the kid is in fact moving relative to the slide, that would be kinetic friction acting on this little kid. So yay, there's the little kid sliding down the slide. And the kid is going that way relative to the slide, so the friction force is going back the other way. It's opposing the motion that's actually showing up here. And here there is a set value, or to be more correct, we model it as a set value. If you go look into the research, you'll see that this is not a simple subject at all, but that's okay. We can model it as a relatively simple subject. To get the value of the friction force in a kinetic situation, you will use the coefficient mu of kinetic friction times the normal force again. And let's talk about why this makes sense. Well, the normal force, the bigger the normal force is, the bigger the friction force is going to be. And that is true both when you're finding the maximum static friction or when you're finding the actual value of kinetic friction. And that sort of makes sense because, you know, the harder you push an object into a surface, take that perpendicular force and you're squashing a surface down, the more the two surfaces are kind of, you know, like interlocking. They're sort of like grabbing in like this. And so the harder it's going to be to sort of slide them past each other this way. So it makes sense, the bigger the normal force is, the bigger the frictional force will be. And this coefficient of friction, so mu, the coefficient, well, what can we tell about that? Well, the first thing we can tell is it's got to be unitless. It has no units of itself, and that's generally what goes on with coefficients. And how we know that that must be true is because the units of the normal force here have to be newtons, because it's a force. And the units of the frictional force here also have to be newtons, because it's a force. And in order for this equation to be true, at least unit-wise, this guy can't have any units, because otherwise, you know, that would mess up. You'd have units times something on this side and just newtons on this side. So, sorry, newtons times something on this side and just newtons on that side. And that can't be true because these are both forces. They gotta have the same units, so no units there. So it's unitless, and it depends on what the surfaces are made of. So the surface materials, you know, are they tire rubber and asphalt, or ice, or I don't know, whatever else, denim, eggs, Teflon, something like that, whatever they're made of. It's going to depend on sort of the roughness or smoothness of those surfaces. So this is kind of a weird dependence. We'll talk a little bit more about that later. And it's going to depend on the conditions. like I said earlier when talking about the coefficient of static friction, if you got tire rubber and asphalt, the coefficient of friction is going to be real different depending on whether it's wet or dry or what's going on. Maybe somebody's poured oil on the road. In that case, a disaster. Friction is not working how we need it to for driving. Okay, so let's talk a little bit about the rough versus smooth. It probably makes sense that the coefficient of friction is going to be bigger if two surfaces are very rough. If the two surfaces are very rough, so they look kind of like this relative to each other, you can imagine like maybe a peak on this surface could sort of jump into a trough on the other surface. So the surfaces maybe would start being drawn like this, and it'd be really hard to sort of swish them back and forth relative to each other because like the two bits of material would be smashing into each other and preventing that side-by-side motion like that. But it also turns out that the opposite is true. So in general, the rougher surfaces are, the bigger the friction force is going to be between them. But if you go the other way, and you make surfaces super duper smooth, like incredibly on the atomic level smooth, and you go in and you carefully clean them so there's no like other little bits of grit and dust and whatever in between them. If you make the situation like this is also going to have very high coefficients of friction. So it'll be really high frictional forces in between these two. And perhaps you might have run across this if you ever had the misfortune of getting two microscope slides and you put a little water between them or saline or something and they stick them together and you try and slide them past each other to get them apart. That's really hard, and it's because they're so smooth relative to each other, and then adding the water in just makes it more, plus it sort of adds in a pressure differential there, which isn't helping. But you can actually use this in a useful way. You can make them so smooth, and the reason why the smoothness helps to increase the friction is because if they get super duper smooth, the molecules over here in one surface will actually start forming bonds with molecules on the other side of the surface and start tearing them apart is what you have to do if you want to move them relative to each other. So the smoother it is, the easier it is for those bonds to form, and the greater the coefficient of friction is. And if you go to a really extreme case where it's just incredibly smooth and incredibly clean, you can actually do what is called cold welding, which is where you make it so smooth, you make the coefficient of friction so big, you make the frictional force so big that they're actually welded together now, those two pieces of material. And it's called cold welding because you don't have to get a big blowtorch and blowtorch them together. And this is also this chemical bond that starts happening between two parts of a surface is also why in general the static coefficient is bigger than the kinetic coefficient for two similar surfaces under similar conditions. If things are static relative to each other, the molecules have a chance of sort of forming these bonds across the surface boundary that doesn't happen when they're moving relative to each other. So that is your overview on friction. In just a moment, we will do an example problem on how you'd use this.